So we're now jumping into the fundamental theorem of calculus. We have gotten into looking at antiderivatives, definite integrals, indefinite integrals. We just ended with some definite integrals. And what we were doing to find these definite integrals, we were taking those rectangles and we were summing them up. And the more rectangles we got, the better estimate we got. And we actually found that we could find that area under the curve by looking at the summation. As the number of rectangles went to infinity and we summed up all those rectangles, that gave us the definite integral, the definition of our definite integral. And we saw that number, that area is a number under, and that represents the area under the curve. It only represents the area under the curve if our function is above the x-axis. If it dips below the x-axis, we'll see that that is what is called the net area, and we'll look at that in a minute. But the fundamental theorem of calculus, it has two parts, and I'm going to go over what our book calls the second part first, and then we'll go over the first part. But what the fundamental theorem of calculus says is, if you have a continuous function f at every point on an interval AB, and capital F, which represents the antiderivative of little f on AB, then we can say that the definite integral from a to b of little f of x is equal to the antiderivative of f of x, which we represent as capital F, from evaluating it at our upper bound, so f of b, minus evaluating at our lower bound. Okay, so this kind of ties in differentiation and integration together. They're actually inverse operations of one another, just like addition and subtractions are inverses of one another, or multiplication and division. We saw that a function and its inverse function, so inverses of one another. And so same thing with antiderivatives and derivatives, integration and differentiation. Okay, so let's look at this formula and let's evaluate the following. Let's say that they wanted us to take the antiderivative from 0 to 2 of x all times x minus 3 dx. Oops, let's move that down. And so before we can take that antiderivative, notice that we don't know how to do that now because of the x times that quantity x minus 3. But just like before we would take derivatives, sometimes we would expand things or we can manipulate it. And so that's exactly what we want to do here. So let's first expand that x to the quantity x minus 3. And so we're looking at the definite integral from 0 to 2 of x squared minus 3x dx. So let's just kind of review, because it's been a little while since we looked at indefinite integrals. But remember, we saw that if we had x raised to the nth power dx, that antiderivative was the opposite. So what we could take the derivative of and get back what we call this integrand x to the n. And so doing the opposite, we added 1 to our exponent instead of subtracting 1, and we divided by that new exponent. In here, we added this constant c for indefinite integrals. We'll see that we don't have to do that for definite integrals. And so let's just use this rule here, the antiderivative. First thing we want to do is we want to find the antiderivative. And so in this case, and remember we denoted that with a capital letter. If we looked at this the antiderivative of x squared minus 3x. Well, adding 1 to our exponent, we got 3. Divide by our new exponent, we get 3, minus, we can keep that coefficient there, 3, and then the antiderivative of the x. So add 1 to our exponent, which is 2, divide by that new exponent of 2. Let's say that we forgot that we didn't have to add the c here, and we just added that c in here. Anyways, so once you find that antiderivative, and the way that we would denote this is that we want to evaluate this on our bounds, and we're looking at f of b, the upper bound minus the lower bound. And so normally I would denote this as x cubed over 3 minus 3x squared over 2. And to denote this, and I'm going to just put the plus c here, but I normally wouldn't do that. To denote that I was going to evaluate this on my bounds, I put the lower bound, I make a vertical line, and I put a lower bound on the right-hand side, bottom. And the upper bound is at the top, that vertical line on that right-hand side. So we want to look at evaluating it at our bounds. So we need to find now this f of our upper bound, which is 2, minus f of our lower bound, which is 0. So all we're doing is we're going back into our function and we're plugging in those values where we see our x. And so plugging into wherever we see our x, we get the following. We get 2 cubed all over 3 minus 3 all times 2 squared all over 2, and then plus the c. So this is our f of 2 value minus our f of 0 value. So now we're just going back into our antiderivative and we're plugging in 0 wherever we see an x. So we have 0 cubed all over 3 minus 3 times 0 squared all over 2 plus c. Okay, so let's clean this up. And so we can clean this up by expanding, doing our arithmetic. So order of operations, 2 cubed gives us 8. And then we have that over 3. And so we get 8 over 3 minus, so 2 squared is 4 times that 3 on top, which is 12, all over 2 plus c. Minus, we'll notice that these first two groupings inside that second parentheses, those are 0, 0 minus 0, and then we have that plus c. But notice the negative, and this is where you have to be careful. You need to always put parentheses around that second evaluation, the bottom bound, because that negative is going to distribute. And so we have minus c here. And so it doesn't matter, whatever c we chose, those c's will always cancel out when we evaluate it. So that goes away. And so I need to figure out what 8/3 minus 12/12 is. And so I need a common denominator. I guess actually 12/12 is 6. So we have 8/3 minus 6. So getting a common denominator of 3. I have 8/3 minus 18/3. Which is equal to negative 10/3, or negative 3 1/3. So notice we got a negative answer in there. And so a negative answer is telling me that if I looked at this graph, either all of my areas underneath the x-axis or most of that area is underneath that x-axis. So let's pull up the graph of that and just talk about it for a second. So notice I just pulled up the graph and we're looking at that parabola, and we were looking at, if we were thinking about it as area, we're thinking about from 0 to 2, what is that area bounded between the x-axis and this curve? If we're talking about area, then what we have to do is we have to find out where our graph is below the x-axis, and we would have to take the absolute value of that sum, or of that negative number. And so in this case, if they ask for area, I know that the area between x squared minus 3x and the x-axis is actually the absolute value, because from 0 to 2, this whole thing fell below the x-axis. I'm just going to call this little f of x dx, which in our case would equal positive 3 1/3. Okay, so that is bringing up the net change. And maybe before we just get into that, let me go through one more example. So now our next example is the integral bounded between 0 and pi of the quantity 1 plus cosine of x and then dx. And so I'm thinking to myself, what would that graph of 1 plus cosine of x look like? Well, I notice that that's going to be the same thing as my graph of cosine of x, but that plus 1 in there is shifting the graph up. And so usually when I break this down, it'll look like this. Normally I'm at 1 when I start with cosine, but I'm shifting that up 1 unit. And so I'm actually starting at 2. And so from there, so my mid value line is actually just shifted up. So this is kind of like where my x-axis would have been if I didn't shift it up. And so I would come back down here and I would hit 1 when I got pi halves. And when I hit pi, I would hit 0. And so we would have this curve that looks like this. So notice that that is all above the x-axis. And so I notice that when I look at this and I find this area in here between 0 and pi, I should have that exact area, and I don't have to worry about this dipping below the curve. So let's go ahead. You always start with taking the antiderivative of your integrand. And so thinking backwards, what would I take the derivative of to get back 1? Well, I would take the derivative of the x to get back 1. And then you think to yourself, what would I take the derivative of to get back positive cosine of x? Well, if I take the derivative of sine of x, that is positive cosine of x. So that would be plus sine x. And then I put this vertical line to tell me I'm going to evaluate this from 0 to pi. So first thing that you want to do is we want to evaluate our upper bound. And then we'll plug in our lower bound minus our lower bound. So if we go in here and we plug in pi wherever we see an x, we get pi plus sine of pi minus parentheses. Now we're going to go in there, we're going to plug in 0 wherever we see an x. So we have 0 plus sine of 0 So pi plus sine of pi. Well, that's just pi. Sine of pi, if you think of your unit circle, pi gets us here on the negative x-axis. Sine is our y value, which is 0. So this is plus 0, minus 0, plus, well, sine of 0. So right here, our y value on the unit circle is also 0. So minus 0. So this is just giving us back pi. So if it asks me to find the area, it's actually the exact same thing as that f of b, the antiderivative of evaluated at b minus the antiderivative evaluated at a. Oops. Well, let's look at one more. Sorry, I keep on saying that. Let's look at one more. Let's say you wanted the definite interval from 0 to 2 pi of sine of x dx. So if I look at this, or maybe if we can always take the derivative or antiderivative first too, but if I looked at this and I graphed my sine function, I start at the origin and I start increasing and I hit +1 at pi halves. At pi, I come back down and I hit the x-axis, 3 pi halves, my y value is -1, and come back up and hit the x-axis at pi halves. Oops. And so if I took the antiderivative of this, antiderivative of sine of x, we just said was cosine of x. All right, so if I take the derivative of cosine, so no, it would be negative cosine of x. So derivative cosine of x is negative sine of x. So the antiderivative of sine of x is negative cosine of x. And we're evaluating this from 0 to 2 pi. So let's go in and plug in our bound. So we have our upper bound, which is 2 pi. So I have negative of cosine of 2 pi minus negative of cosine of 0. Well, 2 pi, cosine of 2 pi, my value is +1, and I have a negative in front of it. So this would be -1 minus, again, cosine of 0 is the same value I'd get back if I'm thinking of the unit circle. And I also get 1, but it's negative in front, so -1. So I have -1 plus 1, which is 0. So this net change, it's basically taking, which I'm going to show you in a second, this area in here. But if I found this area below, it's coming out negative when I'm looking at the definite integral. And so if I'm really talking about area, I have to look at the absolute value of that piece. So for area, f of x equals sine of x bounded between the curve and the x-axis. So the first thing that you actually have to do is you have to find out, is our function crossing that x-axis in that bound, that region it's asking us to find that area? And it is in our case. And if it is, then we got to break it up into multiple different intervals. And we saw that we could do that yesterday with properties of intervals. So what we want to do is we want to actually break this down as the integral from 0 to where it's going to cross the x-axis, pi, of this sine of x. And then we're going to add, because it's going below the x-axis, we're going to add the absolute value. We're starting at pi here, and then we're going to 2 pi of this sine of x. I need to put dx in here, dx. And so we should see that we get back 2 in there. But let's show it really quickly. And so we're looking at the antiderivative of sine of x, which we said was negative cosine of x. This piece has to be evaluated from 0 to 2 pi, plus that absolute value of the antiderivative of sine of x, which is negative cosine of x. We're evaluating this from pi to 2 pi. And so let's go ahead and plug in our bounds. So first we're going to get negative cosine, plugging in pi, minus negative cosine of 0. This plus the absolute value. So now plugging in 2 pi, wherever I saw an x, I get negative cosine of 2 pi minus the negative cosine of pi. And take the absolute value. Okay, so negative cosine of pi, that's negative of -1, minus the negative cosine 0, that's negative 1. Cosine of 0 is 1, and then the negative in front, plus this absolute value. So negative cosine of 2 pi. Well, cosine of 2 pi is 1 with a negative in front, so that's going to give me a -1, minus negative cosine of pi. Well, cosine of pi is -1, so negative of -1. So this gives me -1, negative of -1 is 1 plus 1, plus the absolute value. So -1 minus a negative. So that's going to be -1. So here we have 2 plus the absolute value of -2. So we have 2 plus 2, which gives us 4. So if we wanted to find the area, this area bounded between the curve and the x-axis is going to be +4, and then whatever units we are, quantity squared, unit squared. Okay, so this brings us into what I keep on pushing down, the theorem or definition of the net change. And so the net change in a differentiable function of capital F of x over an interval from a to b is the integral of its rate of change, the antiderivative evaluated at b minus the antiderivative evaluated at a. So basically all they're doing is they're summing all the areas above. They treat as positive, all the area below, it's coming out as negative, and they sum it, and that gives us the net change. And that's basically what we were just doing with all of those definite integrals using that fundamental theorem of calculus. So the next example doesn't tell us just to take the definite integral and evaluate it. It's telling us that it wants us to find that total area between the curve and the x-axis, where our curve is y equals 3x squared minus 3, and we're trying to find that area bounded between x equals -2 and +2. So first thing that you always want to do when you're trying to find that total area, first thing you want to do is you want to find any x-intercepts. So let's first find your x-intercepts, if they exist. So we know that's when our value of y is 0. And so we're looking at when is this 3x squared minus 3 equal to 0. Notice I have a quadratic. I notice I can factor out a 3. And so we have 0 is equal to 3 times the quantity x squared minus 1. I notice x squared minus 1 is a difference of 2 squares, so we can factor that as x minus 1, x plus 1. And so notice that we can see that the graph is crossing the x-axis at x equals 1 and x equals -1. So these values, we want to check to see, are those values actually crossing in between the values that we're looking at the area for? And notice that those are both contained between -2 and 2. And so we're going to have to break this down as multiple different sections. If I look at this, I know that this is a graph below the x-axis. If we kind of think about this, let's just use some algebra. Let's find our vertex. So we can find our vertex. This is our x value. One way to do it is -b over 2a. So notice that we don't have a b value here, so this is actually equal to 0. And then I can find my y-intercept, or not my y-intercept. I can find, it actually is, but I can find that y value of my vertex by plugging in this value. So vertex is at -b 2a, and then evaluating at that -b 2a. So 0, and then if I plug in 0 back into the original equation, I get back -3. We saw that it crossed the x-axis at 1 and -1. Oops. So we have this parabola in here. And then we could actually quickly figure out what our y value is at 2. If we plugged it in here, 2 squared is 4, 4 times 3 is 12, 12 minus 3 is 9. Let's just say that this is 9. Same thing, when I plug in -2, I would get back 9. So I'm looking at this area in here. I'm looking at this area in here. And those are above the x-axis. And I'm looking at the area that's below the x-axis. So it looks like I got to split this up into 3 separate intervals. I need to look at the interval starting at -2 until I hit my x-axis, which is -1 of this 3x squared minus 3 dx. Plus what I get below the x-axis, but I have to put the absolute value around that. And so my bound I'm starting that is at -1 to +1 of this 3x squared minus 3 dx. In my absolute value, plus the area from 1 to 2 of this 3x squared minus 3 dx. So we could actually use information about symmetry in here. We could technically, I see that because this is a parabola and that axis of symmetry is my y-axis, that same area on the left-hand side is going to be the same area on the right-hand side if it's equal distance from that origin or the vertex, axis of symmetry. So let's just go in and do our work. If we want to use that fact, we can just find one of these. If you're going to do that, though, on an exam, explain that that's the reasoning behind that. Notice when we take the antiderivative or integrand, we're always going to get the same thing for each of those intervals. And so it's not too bad. The antiderivative of 3x squared, that's 3x cubed over 3, minus the antiderivative of 3, which is 3x. And we're evaluating that from -2 to -1. Plus that absolute value, again, we have that same thing, 3x cubed over 3 minus 3x. This one is between -1 and 1, and we're taking the absolute value of that sum. Plus 3x cubed over 3 plus 3x, actually minus 3x. And evaluating that from 1 to 2. Okay, so going in and plugging in our values. If I plug in -1 wherever I see an x, and notice I'm going to, before I do that, I'm going to cancel out my 3's. So I get -1 cubed. -1 cubed gives me -1 back, minus 3 times -1, which is actually plus, just do this, plus 3. So it's that first part minus the second part. So plugging in -2, where I see an x, -2 cubed is -8. And then I have -3 times -2, so plus 2. Plus the absolute value, plugging in 1. So if I plug in 1, 1 cubed is 1, minus 3 times 1 is 3, minus, we actually just plugged in this -1 in here, right? So that's the same thing as -1 plus 3, which is 2. Plus, so plugging in 2. So let's go back in and plug in 2. Wherever we see an x, we got 2 cubed. That gives me 8 minus 3 times 2, which is 6, minus, now let's go in and plug in 1 wherever you see an x. Again, we already did that work over here. But if you don't see that, we have 1 cubed, which is 1, minus 3 times 1, which is 3. So this gives us negative 1 plus 3 is 2, minus, but in here, negative 8 plus 2. So that's negative 6. And negative, that's plus 6. Plus the absolute value. So this is negative 2 minus 2. Plus, so 8 minus 6, that gives me 2, minus 1 minus 3 is negative 2. So with a negative in front, that is also 2. Guess those aren't the same areas. That doesn't make sense to me. Just make sure when we plug in negative 2, I see already that's where I'm wrong. When I plug in negative 2 here, that should have given me negative 3 times negative 2 is plus 6. So right here, negative 8 plus 6, that's negative 2. And this negative and a negative 2 gives me plus 2. There we go. So me explaining that those had to be the same, I knew I did some error in there because I wasn't getting the same thing on both sides. So here I have 4 plus absolute value of negative 4 is 4 plus 2 plus 2, which is 4. So our total area is equal to 12 units squared.